All right, let's take a look at question number 2 in our homework last night, page 491. A 1,200 kilogram car attempting to run a red light strikes a stationary 1350 kilogram car waiting to make a turn. Skid marks show that after the collision, the 1350 was going at east of north, and the other one was going at west of north. What was the velocity of the 1,200 kilogram car just before the collision? This is a little bit of a different one than, say, question number 1. We've got 2 funny angles in here. Okay, we know that when we have funny angles, we want to get rid of those funny angles. So in the end, we're going to have to get rid of 2 of them here. Let's draw the picture out here. We know more about after the collision than we do before the collision, but we do know that the 1,350 kilogram object before the collision, we'll call it object number 2, is at rest. So we'll say V is equal to 0 meters per second for that second object before the collision. Now after the collision again, the 1350, object number 2, goes east of north. So we'll say object number 2 is up here at 8.30 meters per second, still a mass of 1,350 kilograms, and the angle would be 55.2 degrees east of north. Do you see why that's east of north? The angle's always got to be measured from an axis, north, south, east, or west. This one's measured from north, so it's going to be something of north. Well, the only logical one that it can be is east of north because it's going east and north. So this is 5.2 degrees east of north. The other one is 36.8 degrees west of north, so it's going to be up here. 36.8 degrees. It's also measured from the north axis, but it's west of north instead of east of north. It's the other vehicle. That's object number 1. It's my 1,200 kilogram object, and it's going at 12.8 meters per second. Now, object number 1 before the collision presumably is going to be going up here somewhere with a mass of 1,200 kilograms with a speed of whatever and direction of, we're not really sure. Okay, it could be going straight north, or it could be going at some kind of angle to produce this. Does that make sense? Bottom line is we don't know what direction it's going. We don't know what speed it's going at. We got to find that. So let's do what we do. Let's break it up into components. The x component, we're going to say pi is equal to pf. How many objects do we have before this collision takes place? We got 2. We don't know which way the first one is going. We don't know what its velocity is, but we do know that we have 2 objects before this collision takes place. So we're going to have 2 terms, m1 v1i plus m2 v2i. After the collision, we also have 2 objects, so we're going to say m1 v1f plus m2 v2f. Do the masses cancel here? No. Jay says no. They don't cancel because they're not the same mass. I think one of the questions we did yesterday, the masses did cancel, if I remember. Okay. Why did they cancel yesterday? Because they had the same mass. Okay. If they do, then get rid of it. Save yourself a little bit of effort and a little bit of time. If they don't cancel them out. Don't panic about it. It's not harder. It's just a tiny little bit of extra time that it takes us to do it when the masses don't cancel. All right, let's start plugging some numbers in here. Do we know what the value of m1 is? We do. It's 1,200 kilograms. We don't know what the value of v1i is. Okay? It has conceivably an x component. What's its value? We have no idea. v2i we know is 0 because it's at rest, so we can get rid of that. Bless you. m1 again is 1,200 kilograms. Do we know what v1f is? We take a look at this diagram up top here. Do we know what v1f is? We don't. We don't. Says up on the board there, the diagram, that it's 12.8 meters per second. Why can't we use that 12.8 meters per second and substitute it in for v1f here? Ashton? Right, it's at an angle. And that speed that we're given is at that angle. We're looking for just the x component here, so we need to find the x component. While we're at it, we might as well find the y component. Let's redraw it to do that. Let's say we've got 55.2 degrees. We've got 8.30 meters per second. This is going to be the x side, and this is going to be the y side. Which side of the triangle is x? Sorry, this is object number 2, isn't it? Okay, we're going to have to do that eventually anyways, but let's go over and do the first one, the one that we're looking for first. This is 36.8 degrees. This is x, this is y, and this is 12.8 meters per second. Which side of the triangle is the x component? Is it opposite, adjacent, or hypotenuse? Shane? Focus, okay. Which side of the triangle is the x component, opposite, adjacent, or hypotenuse? It's the opposite side. So which trig function involves opposite side and the hypotenuse, the value that I already have? Which one is it, Jordan? Good. Sine. So we're going to say sine 36.8 degrees is equal to opposite over hypotenuse. What's the value of 12.8 sine 36? Somebody have that? $7.66775. Just 1 7 there. 7.6675 meters per second. Thank you. Now we got to do the x component, the y component. The y component must be the adjacent side if we just solve for the opposite side. So we're going to use cosine to find that. Cosine 36.8 degrees is equal to the y component over 12.8 meters per second. What does the y component work out to be there? 12.8 cosine 36.8. $10.24936 meters per second. Thank you. So we've just found the x and y components of object number 1 after the collision has taken place. Let's sub in V1F. Which one is V1F here? 7.66 or 10.24? Which one do I put in there? Carson, which one do I put in there? 7.66 or 10.24? Which one do I put in there? Jonathan? Right, 7.66. We're going to put in the x component of object number 1. We just analyzed object number 1 to get rid of that funny angle, that 36.8. We analyzed the x by using sine, the y by using cos. We found the x to be 7.6675, so we're subbing that in for the x component down here. The value of mass 2 was, what is mass 2? 1,350 kilograms times V2F. We don't know what V2F is either. So we got to do the same thing we did with the last one, with V1F. We're going to do the same thing with V2F. So let's go back up here, do our little aside thing, figure out what the x component is and what the y component is. Once again, x is the opposite side, so we're going to say sine 55.2 is equal to x over 8.30. What does that work out to be? 8.3 times sine 55.2. 6.81553. Thank you. While we're at it, we might as well find the y component. We'll say cosine 55.2 is equal to y over 8.30. And what does the y component equal? 8.3 cos 55.2? It's 4.73692. Thank you. So we've just gotten rid of that 55.2 now and replaced it with a 6.8 and a 4.7. What's the value of V2F that we plug in here? Good, 6.81553. Okay, let's do the math here. What does V1I work out to be when we do that math? Get the number on the right-hand side, divide it by 1,200. V1I works out to be what? You know what? We made a mistake here. Object number 1 is moving which way? Yeah, we need positive and negative because object number 1 is moving to the left, right? Up and to the left. So this is going to be a negative value. Now, when we do that, what do we end up getting? Pretty small number, I think. What'd you get there, Drew? Negative 2.75. 2.875 times 10 to the negative 5. All right, that's a really small speed, right? Really small speed. So the x component of this initial velocity is really, really small. Let's do the y component now and see if it's any bigger or it's similar magnitude here. The y component is going to be found by the same basic method. It's going to be a little bit easier for us because we've already found the x and y components of those those vectors after the collision has taken place. We got two objects before, m1 v1I plus m2 v2I equals two objects after, m1 v1f plus m2 v2f. M1 is 1200 times v1I. v2I is again 0 because we're told that it's at rest. M1 is 1200. Tell me what v1f is. Let's look at the diagram up here, our little asides that are boxed off there. Tell me what v1f is. Shane, what's v1f for the y component? Cole? What's v1f? 10.24936 meters per second. Good. Is it positive or negative, Cole? It's positive because it's up, right? All right, M2 is 1350 again, same as it was for the x component. But V2F this time, V2F for the y component is what? V2F y component. Brianna? Good. 4.73692. And it's going to be positive because it's up. When we calculate V1I here, I think we're going to end up getting 15.6 meters per second. Is that right? All right. What should we technically do at this point now that we've got an x component and a y component? We should combine them, right? We should combine them by drawing a vector diagram and then doing the Pythagorean theorem in the inverse tan function of opposite over adjacent. But when we combine something that's 10 to the minus 5 with something that's 10 to the positive 1, what are we going to end up getting? You combine this with this, and it should be even longer, we end up getting this. So we don't even need to do the Pythagorean theorem here. The y component is so much bigger than the x component. When we do the math, we're going to end up with, to 3 digits at least, the same value. It's kind of like a question that we did yesterday, right? Remember we did the question yesterday where the coal was coming down and hitting the hopper car? And there was a final y velocity involved there, but it was so small compared to the final x velocity that we really didn't need to pay attention to it. Well, this initial x velocity is so small compared to the initial y velocity that we really don't even need to do anything with it. If you're ever unsure if it's small enough to ignore, then just do the Pythagorean theorem. Find out, figure it out. But when you're talking about a difference of 10 to the 6, which is what we've got here, 10 to the minus 5 to 10 to the 1, do the Pythagorean theorem, it's going to end up to be the 15.6 meters per second. Okay? So basically, this object is moving upwards before the collision has taken place. I'm going to take a look at one multiple choice question here right now. This is multiple choice question number 37. I'd like to give you about 2 minutes to work on that right now, and then we'll take a look at it as a class when we're finished that. I'll leave this information actually up on the page here. It doesn't actually have the question there, though, so that we can't see the data and the question at the same time. So I'll just essentially tell you what they're asking for. They're looking for the magnitude of the momentum of the third piece. What do those little signs mean? What do those little vertical lines mean on either side of the momentum C? Absolute value. So we're looking for the magnitude of the momentum here. They're not asking for the direction, although you can imagine if we can find the magnitude, it's pretty easy to find the direction after that, right? They're just saving us a little bit of bother. We don't have to do both. So let's get the magnitude of the momentum, not the direction. And remember, it's the magnitude of the momentum, not the magnitude of the velocity. But get one, it's not very hard to find the other. Okay, let's see what you can do over the next 2 minutes, okay? Now let's take a look at the question here now. It says a glass ornament of mass 575 grams sitting on a table is subjected to a resonant frequency of 440 hertz. The ornament breaks into 3 pieces that travel horizontally across the tabletop. Mass is 168 and 212. What's the momentum of the third piece? Or at least what's the magnitude of the momentum of the third piece? We know what to do here, right? This is a conservation of momentum problem because we've got an explosion. But because we've got both x and y components, we've got to break it up into those components. Now, the first thing that I kind of see here is that they give us a diagram, which is kind of nice. But that tells us quite clearly that we've got 2 different dimensions. We've got part of it on the x-axis, part of it on the y-axis. A is okay. It's only on the x-axis, but B is at 60 degrees north of west. So let's change that. Let's get rid of that funny angle. Let's redraw B, and let's get the x and y components for B. We got 60 degrees here. This is the x. This is the y. Does that make sense? Could we use the 120? We could, and it would work. But my suggestion is to always go with the angle that's less than 90 degrees. If you start going with the angle that's bigger than 90 degrees, then you're going to start getting negatives and positives with your answer when you do trig functions. Okay, we want to, and that's not necessarily a bad thing, but we're used to just looking at this and saying, oh, it's left, therefore the x component is negative. If you go cosine 120, you're going to get negative. And if you try to make it negative on top of that, then you're going to end up making it positive. So my suggestion is just ignore the big angles. Look at the small angles. Look at the angle that's less than 90 degrees and use your sine and cosine with that. Now, what number do I put right here? I put 212, 9, or 1.91. I got a couple of options here, really. What do you want to use? Who got the question correct? Okay, Kim, what did you use? Did you use the 1.91 or the 9.00? 9.00. Okay, Jade, what did you use? Okay, 1.91. What did you use? 1.91. Either one of them are okay. If you use 1.91, it's a little less work. Are we allowed to use both of them? Of course we are. They're both vectors, so we can find the x and y components of either a velocity or a momentum. The reason that I'm going to find the x and y components of a momentum, the way that Jay did it, is because we're looking for a final momentum. It's going to allow us to do a tiny bit less work. It's not more right. It's just a little bit less work. So let's get those x and y components here now, okay? Let's say cosine 60 degrees is equal to x, the adjacent side, over the hypotenuse of 1.91. What's that going to equal? Cosine 60 is 0.5 times 1.91 is 0.955. 0.955. Remember, that's momentum, not velocity. Let's do the y component now. Sine 60 degrees is equal to the y component over 1.91. What does that equal, Jade? 1.65416. Thank you. Once again, we're dealing with momentum here, so it's kilograms meters per second. Now let's do our conservation of momentum thing. X and y like we always do. If you did it like Kim, you're going to say the initial momentum is 0 because it's at rest on this tabletop before the explosion takes place. And you're going to say the final momentum is m1 v1f plus m2 v2f plus m3 v3f. There's nothing wrong with that. That's absolutely correct. But what happens when you multiply 0.212 by 9 meters per second or 0.168 by 15 meters per second? You end up getting the value that's already given to us. They're giving us the momentum. So we don't need to bother writing m1, v1 and multiplying those together. We already have the value of m1, v1. The value of m1, v1 final is 2.52. The value of m2, v2 final for the x component is 0.955. It's actually negative because it's to the left. And we can leave in m3, v3f if we want, but since we're looking for the final momentum, not velocity, we can just do that. Kim, does that make sense? It's a bit of a shortcut. Like I said, it's no better. It's no more correct. It's just a little bit less work. Remember I told you yesterday that usually when you get a two-dimensional thing like this in multiple choice, there's usually some kind of shortcut. If you spot it, that's great. If you don't, then do it the long way. Just takes you a little bit more time, that's all. What do we end up getting for P3F X component here? Didn't do that? Okay. Did it a little bit differently? Okay. Yeah. Negative 1.565. And that would be, since it's momentum, kilograms meters per second. What's the other set of units, by the way, that I could use for momentum besides kilograms meters per second? Newton seconds. Let's take a look at the y component now. The initial is equal to the final. The initial is 0 again. The final y momentum of the first one is 0. The final y momentum of the second one is 1.65416. And the y component of the third one is not sure. Solve for that, works out to be negative 1.65416 kilograms meters per second. So we want to combine those now. We got 1.565 to the left. We've got 1.65416 downwards. When we solve for that, when we use the Pythagorean theorem to solve for the hypotenuse, it's going to give us not the final velocity this time, but the final momentum. Does it make sense, everybody, that I'm allowed to do the same thing with momentum vector as I did with velocity vector? I can do it with whatever vector I want. You can take components of whatever vector you want, including velocity, momentum. Now, Jay did it a little bit differently. I think I know how he did it, and I think it's okay. There's a little bit more of a shortcut that you can take with this. Jay, was your way a little bit shorter than this even still? Okay. And that's okay, but I'm not going to talk about that with everybody because I think if I show people that shortcut, then they might be able to do it, but not really understand it. I think you understand it. I think you understand why that's okay. I don't want people to not understand it because when you get a question that's just the tiniest bit different, what do you do then? Right? Jade, that solution makes sense to you though too? Okay, if you need to do that sometime. What do we end up getting for P, by the way? 2 point. Shouldn't be 11. It's not 11. We're not going to take 1.5 and 1.6 and get 11 out of it. 2.27. This was multiple choice. Let's see if that's an option. We got 2.28, so there must have been a rounding issue there. But is that okay? There's a question that's fairly similar to that on tomorrow's test, an explosion question like that where it breaks up into 3 pieces and stuff. I can't remember if you're asked for a velocity or a momentum or what, but it's fairly similar to that. Okay, the last little thing that I want to do here, and this is not new to us, this is just revisiting something that we've already done. We're actually going to do a check and reflect question as an example. It's question number 6 on page 499. It's not an example in your textbook, but we're going to do it as an example because I thought it was a good one to do. it asks us for the velocity of the other bumper car immediately after the collision. I want you to tell me whether it's elastic or inelastic. Quick review on that. Who can tell me what the difference is between an elastic collision and an inelastic collision? What's the difference? Brenda, what's the difference between elastic and inelastic? Good. It gets a little confusing with the way we say it, right? In an elastic collision, kinetic energy is conserved. In an inelastic collision, kinetic energy is lost. What about momentum? What about momentum in an inelastic collision? Is momentum still conserved? Yeah. Yes. What about in an elastic collision? Is momentum still conserved? Yes, momentum is always conserved. So we're looking to see here if kinetic energy is the same or if kinetic energy is lost. Let's do that now. It says a stationary 230 kilogram bumper car in a carnival is struck off center from behind by a 255 kilogram bumper car moving to the west. The more massive car bounces off at 0.627, 42 degrees south of west. What's the velocity of the other bumper car immediately after the collision, and is it elastic or inelastic? What's one of the ways that we can sometimes use to determine whether a collision is elastic or inelastic without doing a calculation? Yeah, okay. If it's subatomic, we could usually assume that it's elastic, but I don't think you should. Okay, we should do a calculation nonetheless. But there is one situation that tells us for sure that a collision is not elastic. No, the other way around. Shane? If they stick together, it's inelastic. If they bounce back, it could be elastic, but it could be inelastic. These bounce apart, right? So we don't know whether this is elastic or inelastic. Okay, my guess would be that it's inelastic because we're dealing with bumper cars. But we got to calculate the kinetic energy before and after just to make sure. Okay, let's draw this out so that we can do the first part of it, finding the velocity of the bumper car immediately after the collision. We've got, let's say, car number 1 that has a mass of 255 kilograms. It's moving at 0.843 meters per second to the west. Car number 2 is at rest. It says it's stationary. So we're going to make that 230 kilograms, and we're going to say its velocity is 0 meters per second. Struck off center. So it says the more massive car, that's the 255, car number 1, is going down this way, 42 degrees south of west, and it's going at a velocity of 0.627 meters per second. We can probably make a pretty good guess that car number 2 is going to go up this way somewhere. We want to figure out its velocity. It's the first part of the question, but in the end, if we want to calculate its initial and final kinetic energy, we need its velocity anyways. To do that, we're going to break it up into our components, but you know what? Let's do our little aside thing first. We don't like that funny angle of 42 degrees. Let's get rid of it. This is the x side, this is the y side, this is 0.627. We're going to say cosine 42 degrees is equal to the adjacent side, x, over the hypotenuse, 0.627. And this is just the same thing we've been doing for the last couple of days, right? So far. What do we end up getting for x there? .46595, thank you. We're back to using velocity here, right? So it's meters per second, not kilograms, meters per second. Let's find the y component. It's the opposite side of the triangle, so we're going to say sine 42 degrees is equal to y over 0.627. What do we get for that one? 0.41954. Thank you. All right, now let's do our x's and y's. Pi is equal to Pf. There's two objects before, and there's two objects after. M1 is 255. What's V1i for the x component? Emma, what's V1i for the x component? The initial velocity of object number 1, horizontal. Not 0.46, no. Initial. Good, 0.843. But we're going to make it negative because it's to the left. M2 is a value of 230, V2i is 0, so let's just cross that off. M1 is, again, 255. All of you people not writing right now, tell me what the value of V1F is. What's the value of V1F, Tom? Good. But we're going to make it negative because it's acting to the left here. So negative 0.46595 plus M2 times V2F. M2 is 230 times V2F. We do the math on this when we end up getting negative 0.4180 meters per second. We do the y component. This one's a little bit easier because the initial y component is 0. Object number 1 is moving, but it's not moving on the y direction, the y axis. Object number 2 just isn't moving at all. V1F is negative 4.419544489. We do the math on that one, and we get positive 0.4651. We're going to combine them. We've got 0.4180 to the left. We've got 0.4651 up. And we do the Pythagorean theorem. And for that, we end up getting 0.62537 meters per second. Or we're going to round that to 3 digits, 0.625 meters per second. Anybody else get that? Yes? Good. We can find the angle there fairly easily here. The angle is the inverse tan function of opposite over adjacent. 0.4651 divided by 0.4180. What do we get for that? 41.9 degrees. All right, so we solved the first part of the question here. We found the final velocity of that second object, that second bumper car. 0.625 at an angle of 41.9 degrees. Now, how do we determine whether this is elastic or inelastic? Do we have a whole lot more work to do? X and Y components of kinetic energy this time? No, we don't, actually. That's what I want. I mean, in the end, we've already done this stuff. We've already done kinetic energy and the whole idea of elastic and inelastic collisions. The only reason I'm revisiting it right now, after we've done two-dimensional collisions, is not because it's any different whatsoever from what we've already done. In fact, that's just my point. It's exactly what we've already done. Just because we've done two-dimensional collisions doesn't change a thing for elastic and inelastic collisions. You still have to figure out the initial kinetic energy, but we're not going to break it into components. EKI is simply equal to 1/2 m1 v1i squared plus 1/2 m2 v2i squared. Why are we not breaking kinetic energy into components? We had to break momentum into components, but not kinetic energy, because momentum is a blank and kinetic energy is a blank. Right. Momentum is a vector, kinetic energy is a scalar. So we don't need to break it into components. In fact, it's wrong to break it into components. The kinetic energy of object number 1 before the collision is 1/2 of 255 times 0.843 squared. Notice I even dropped the negative there. I don't care if it's negative. I don't care what direction it is. We're talking about speed here. The kinetic energy of object number 2 is 0 because object number 2 is at rest. When we calculate this, we end up getting 90.6 joules for the initial kinetic energy. Now let's do the same thing for the final kinetic energy. EKF is equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. How do we do this whole 0.627 at 42 degrees? How do we include the angle here? If we're not breaking it into components, how do we include the angle? Two-word answer. We don't. Why not? Because it's a scalar. Right? The point is, it's exactly the same as the questions that we've already done with elastic and inelastic collisions. Just take the final speed, 0.627 meters per second. I don't care if it's 42 degrees or 89 degrees. I don't care if it's left or right. I don't care if it's up or down. Second mass here was 230. And the second speed we've already calculated is 0.62537. Don't forget to square that. When we do the math on this, we end up getting 95.1 joules. There's a problem with that. The final kinetic energy shouldn't be more than the initial kinetic energy. This question, it appears, was poorly constructed so that it worked for calculating a final velocity, but it didn't work in terms of a kinetic energy analysis. And I'm sorry for that. I didn't catch that before I gave it to you here today. In the end, if you get something like that on a test tomorrow, if you find the initial kinetic energy is less than the final kinetic energy on a test tomorrow, you've made a mistake, because I can guarantee you the question won't be poorly constructed like that. Does that make sense? We go through the exact same analysis. Okay, we don't change the analysis. We just trust that the question is a better question, where the final kinetic energy would be less than, probably less than, the initial kinetic energy. Certainly not more. All right. I'd like you to take a look at one question on page 496. This one is quite a bit less work because we don't need to worry about finding the final speed. We're given the final speed. This is just a straightforward EKI, EKF. And you're going to find in this one that it works because this question was designed to be a kinetic energy question, an elastic inelastic question. So take a couple minutes, solve this question. I don't care the fact that it's 252 degrees and 332. I'm not even going to explain what those angles mean, because in the end, when you're doing kinetic energy, they don't matter. Do it like you did a few weeks ago when we were just doing one-dimensional problems, okay? And we'll take a look at it in a couple minutes. How do we know it's going to be inelastic? Without doing a calculation, they don't separate. They stick together. But we're still going to do a calculation here. Our calculation is going to be a kinetic energy calculation. EKI is 1/2 m1 v1i squared plus 1/2 m2 v2i squared. Don't forget to square those v's. Fairly common mistake. We've got 1/2 of 0.168 times 45. I don't care that it's 252 degrees. It's irrelevant. Plus 1/2 of 82.0 times 0.200. Just because it's 0 degrees doesn't mean it doesn't count. What do we end up getting for the initial kinetic energy there to 3 significant digits? Someone's got to have that already. 171? I got 131 over here. 173. 171? 171.74, but we're going to round this to 3 significant digits, so it's 171 joules. That's my EKI. EKF is 1/2 of mv squared. Just one term here because there's only one object. The total mass is going to be 82.168 times the final speed, 0.192. I don't care that it's 333 degrees. It's irrelevant. What do we end up getting for the final kinetic energy? Nobody wants to speak up here because of the disagreement over the last one? 1.51? All right. That's a pretty clear indication that it is what type of a collision? It's inelastic, right? We knew it was going to be inelastic, but calculation just verified. If you wanted to find out what percent of kinetic energy is retained, we would say 1.51 over 171, because that's how much is left, right? And it would multiply that by 100. Okay? That's a little bit less important than this calculation right here to tell us that it's elastic or inelastic. Okay? Would you agree that this is not new? With what we did today is exactly what we did here a couple weeks ago with kinetic energy, elastic and inelastic? Again, that's just my point. We didn't even need to do this today because we've already done it. I just wanted to point out that it's not different, because my fear, if you encounter something like this with 2 dimensions, is that you would try to break it up into x and y components and do something different than we've already done with this. You don't need to do that. Courtney? Yeah, if they hadn't given you the final velocity, then you would have to find it, and then you'd have to do a 2-dimensional conservation of momentum. You can't drop the 2-dimension with momentum, the x and the y with momentum, because it's a vector. But with kinetic energy, you don't. It's as if it's not 2-dimensional, it's just 1-dimensional. Okay? Is that good? You guys going to ace this test tomorrow? Absolutely. Absolutely we are. Good?